information is.
Okay. So now this is full screen. If you go here to diver.net/USC, you can download a copy of the slides. Okay, so it's kind of general topics. So first thing I want to talk about is Kelvin resistance measurements. I don't know if any of you've ever heard of Kelvin resistance measurements or 4-point resistance measurements. Anyway, so what a Kelvin resistance measurement is where the force and the sense leads are separate. Now, if you look at the meters, the HP multimeters back there, you'll see that they have 4 inputs, and one says 4 ohm sense on it. Okay, and the idea is here that if okay, so anyway, your leads always have, test leads always have voltage drop. So, you know, when you measure a resistance, the meter puts out some current, and there's a voltage drop on those leads. And that causes an error, especially when you're measuring low resistances. Okay, and so when you just, you know, the leads may be half an ohm or so of resistance. Contact resistance when you connect to something can be milliohms to hundreds of milliohms, and all this causes error. So what you could do is you could do a 4-point measurement in which the force and the sense are different. And that's called a Kelvin measurement. So if you look on those on that meter, there's a mode called four wire ohms. And what that does is it separates the current source into one pair of connections and the voltage source into another pair of connections, or the voltage sense to another pair of connections. So if you look at the schematic down there on the lower right, you can see that I have a current source that's forcing current, and I'm trying to measure just that R DUT in the middle. And everything, there's contact resistance, wire resistance. Okay, but now if the voltage measurement part draws no current, or essentially no current, so let's say the voltage measurement input impedance is going to be like 10 to the 12th ohm, so it's going to essentially draw no current. You're going to, the voltage you sense across that resistor is going to be exactly IR. And it doesn't matter that you have all these other resistances in there, you're going, the measurement you're going to get is the right amount. So generally, if you're measuring anything on the order of 100 ohms or smaller, and you want to get an accurate measurement, you need to go to a Kelvin measurement. All right. And so this is called a 4-wire ohms measurement. But in general, you can, there's a broader definition of a Kelvin measurement is one in which the voltage sense part is separate from what else is going on. So you're sensing the voltage through leads that draw no current. So you always get an accurate measurement of voltage. There. So here are what's called Kelvin leads. And so here, I brought some for show and tell. These are, you notice there's 2 clips on each lead. So one goes into the force, one goes into the sense, one goes into the force. So you can clip these onto your resistor and you get the exact measurement between those points because the current's being forced in from one side, the voltage is being forced in from the other. Or if you're poking around, let's say on a PCB trace, you're trying to measure the resistance of the PCB trace. The issue will be that the contact resistance is going to screw you up. Often the contact resistance, if you're just measuring with a single probe, will be bigger than the resistance you're trying to measure. So they make these things called Kelvin 2-point probes. So one actually goes into the force, one actually goes to the sense, And you could poke it down on your PCB and get exact resistance measurements. Or, okay. There we go. So other instruments have what I call Kelvin input. Almost every power supply has a force and sense terminals. Typically, they're on the back. So you look here at the top left. This is an HP power supply. I bought this off of Craigslist a couple months ago. And if you look, and then you turn around on the back, you see there's some terminals where it's got force and sense. So the force is where the power comes out of the power supply. And then the sense is where it senses the voltage. Okay, and so normally those are hooked up. So when you normally use a power supply and you put the leads on something, you have voltage drop across the leads and that leads drops. But if you want to regulate the voltage, let's say exactly at your circuit, you hook up the force and the sense lead separate. So you pull off those jumpers and then you cut and you hook that up to your circuit and you can sense the voltage right at where you're trying to regulate. If you look at this power supply I have over here, this is the English power supply I bought off of eBay. And you'll notice down here at the right, it's got some sense lead inputs. So you can, instead of going to the back, you can hook up to the front and then the switch down there local remote will let you sense the voltage in the power supply or at your circuit. And that eliminates, that way you can regulate the voltage going right into your circuit and it takes care of whatever IR drop there is in the leads. And then down at the bottom is a force measure unit, which is another, it's a 4-quadrant power supply. It'll force current or voltage plus or minus. And again, it's got separate things. So it has a Kelvin measure. So here's an example where I actually used a Kelvin measurement, a story. So about 20 years ago, at work, I replaced a silicon Schottky diode in a limiter circuit for a hemped LNA, where a hemp's a 3,5 FET, a gas FET in this case. And I replaced it, the silicon Schottky diode with an indium phosphide Schottky diode. The issue with the silicon Schottky diodes, so when they make the silicon Schottky diodes, they actually just relied on background doping in the chamber to dope a certain layer in the diodes. And so their resistance varied all over the place. Okay, now the indium phosphide diodes are MBE growth. The layers are very exact and consistent across the wafer. Okay, but I needed to know exactly what the resistance was on every diode. And that resistance is a couple ohms. And so we did that at wafer probe. Now to do that, the only way you can do that is with a Kelvin measurement. Otherwise, you can't measure a resistance that low without a Kelvin measurement. Okay, so you can see on the schematic there, I put four pads on the diode. I used a current source across two and then measured the voltage across the other two. And then by doing sweeps, if you do this, this left indication over on the side is 1 over GM versus 1 over IC. And you do, you take some points and fit that intercept exactly gives you the series resistance of the diode. And then here, if you look at log IV, log I on the x-axis and the voltage on the diode on the y-axis, you'll get a straight line of lower currents. The intercept of that line is the saturation current of the diode. The slope of that line gives you the ideality factor of the diode. So with this Kelvin measurement, I could get the exact parameters for every diode. Okay, and so and all these diodes had row column markers on them, unlike the silicon diodes, which have no markers. And so they knew exactly what they got. So each wafer had like 20,000 parts on it. These things were small. and they measured every one, and they have that data. And now Northrop Grumman has these, and they'll probably be using these diodes after I'm dead. There's so many I believe for. Yes.
That's really cool.
Okay, so, but I just wanted to give you a story of why this is important. You couldn't do this measurement without doing a Kelvin measurement.
Oh. Do you need water or anything?
No.
Then you need to let me know.
Okay, so let's talk about metrology standards. How do you know what you're measuring is the same as what somebody else is measuring? Okay, well, so it turns out every country, not every country, but most countries have a department that it's called, years ago, when they first started, 150 years ago or 200 years ago, it was weights and measures. Because back then they just wanted to make sure that, if you got a pound here and a pound there, it was the same. But now they have standards for all kinds of things. And then there's international conferences where they agree on how to measure these standards. And different countries have their standards agency. So in the US, it's the National Institute of Standards and Technology. In China, it's NIM. All these links in the thing I gave in the notes are clickable.
Oh, that's cool.
Okay, so it turns out for electrical stuff, there used to be many vendors that did this, but due to corporate consolidation, there's really only 3 big ones in the world now that make the instruments that are used to calibrate other instruments. There's Fluke, which is now, it's owned by a company, it's the same company that owns Tektronix and Keithley and Pomona Electronics. They're all the same company, they've all been bought by a bigger company. Yokogawa in Japan, instruments, and Yokogawa also is a contract manufacturer for Keysight. Many of almost all the semiconductor measurement instruments that Keysight sells are actually manufactured by Yokogawa. But they do the calibration instruments. And then Tukia is the manufacturer in China that does things. So when you send your meter into for the check calibration, they use instruments from these guys. And then the standards in these instruments are checked somehow against the national standards. Because, often, let's say in the US, if you're doing a government contract, they want NIST traceable calibrations that go back to, so you can verify that your measurements are within so much of the National Institute of Standards. Okay, this didn't change. There we go. So let's talk about time and frequency standards. Originally, there was the way you calibrated time as frequency, and this still exists, is different countries would have radio stations and their frequency was exact. In the US, it's WWV on the chart here. Canada's got one. A lot of countries have those. And those are the frequencies they broadcast on. And those frequencies are exact. Okay.
That's cool.
Okay. And so what you could do is you could take a shortwave radio and then you tune that station in on the shortwave radio.
Okay.
Then you take your signal generator and you either tune your signal generator to that frequency or a subharmonic. So it's a harmonic and that frequency is showing up at the same frequency. And then you'll get a beat frequency, a tone. And then you adjust the generator until the tone goes to DC below what you hit. And then your generator is exactly on that frequency.
So that's how you can calibrate it.
That's how stuff used to be done. Okay.
That's cool.
Okay, and you can still do it that way.
Yeah.
Okay, and so if you don't have anything, if you've just got a shortwave radio at home and a signal generator, you can do that.
So is this sometimes because we were talking about ham radio and how there's some people, do they do that or?
That's one way to calibrate the radio. Most of them use the, I'll go into,
Okay, yeah.
we're
Just
getting,
curious,
we're
yeah.
getting there. Okay, that was the way it was done for like 100
For a
years.
long time.
And these radio stations still exist and you can still
They
do it.
still are there, just in
Yeah.
case. Okay.
Okay. So inside almost every test instrument that measures or sources a frequency or time signal. So oscilloscopes measure time, spectrum analyzers measure signals versus frequency, signal generators output a frequency. They have some sort of frequency standard inside. Okay. So typically, you know, if it's a cheap instrument, it'll just be a crystal oscillator. Okay, so in most instruments, the first option is what's called the TCXO, where X stands for crystal and TC stands for temperature compensated. And that's the default standard for most instruments, okay? And that's got, those usually have pretty good specs on frequency and drift with temperature and time. Okay, then the next level is called an OCXO, in which that's an oven compensated crystal oscillator. And those typically have 1 to 2 orders of magnitude better stability than you get with a temperature compensated crystal oscillator. And that scope from Siglet they sent you has the OCXO option. So it's got these typically are extra money, so they charge you extra for this. You know, they'll charge you $500 to $100 to $1,000. Probably only costs them about $100 to do, but that's how they make their money on the options. And then let's say a laboratory standard, okay, or you know, if you had to have a standard where you didn't have a verification, some way to lock it to something. They do an oven in an oven. So you have your ovenized thing in another oven so that the oven doesn't see temperature changes. Okay. Now, most modern test equipment, it's, you know, above, you know, mid-level to high-end test equipment will have a 10 megahertz reference oscillator in it. They'll also have a way to output that 10 megahertz reference and input the 10 megahertz reference. And so let's say you have one instrument that's got this really nifty reference built in. You can take that out and feed it into your next one. And you can take the output of that one and feed it into your next one. So you can use that reference to lock all your instruments. And besides doing that, then all your instruments are frequency locked. So a frequency on one instrument will match the frequency on the next instrument. Okay, so if you look on the back of some of this road.
Options lock.
What?
It says options lock. No, that's really cool. So you can get a shared frequency.
Yes.
I didn't know that.
Yes.
Match them.
Yes. So if you look at this Road and Schwartz stuff or the Siglet thing, and that all has this stuff on there.
Very cool.
Okay. Let's see. Okay. So the modern way this is done now is what's and calibration labs use, and they use what's called a GPS disciplined oscillator. Okay, so the actual time standard is called an atomic clock. It's based on like a cesium oscillator or something else. The National Bureau of Standards keeps that. Okay, but they also put those in GPS satellites because the exact time and position of those is incredibly important. Okay. And so what a GPS disciplined oscillator is it shows you here the block diagram of the oscillator. So there's a GPS receiver, and then that goes into a time measurement system. And so the GPS may output, let's say, like a pulse every 1/10 of a second. And then you have an oven controlled crystal oscillator in this thing. And oops, I didn't mean to go. How'd I go? Is this got a touch screen?
Oh, yeah, sorry, might jump,
Okay,
just
yeah,
use the mouse to go backwards.
yeah.
You went too far, sorry about
Okay, I'm
that.
sorry, yeah. Okay,
I
yeah, I'm
forgot
sorry,
to
I
tell
touched
you.
the screen and it jumped. Okay, I didn't know this had
I
a
was
touch
surprised
screen.
you.
Okay, okay, and so, the, there's a measurements and then that crystal controlled, oven controlled crystal oscillator gets divided down and also puts a time signal, and then those are compared and with a microcontroller. So it's kind of like a phase lock loop, but much slower than a phase lock loop. Okay, and then that goes back and that will digitally adjust the frequency of the crystal oscillator. Because you can put a capacitance across a crystal, and as you adjust that capacitance, you can get a very small change in the crystal oscillation frequency. And so they make a digitally adjustable crystal oscillator. Okay. So and the GPS DSOs are built in. Every cell phone tower has one. That's why your cell phone is always has the right time, and the time and frequency of the cell phone towers has to exactly match for them to do the smooth handoff. And frequent, their frequencies have to be exact and the time have to match. So as you move around, that handout happens. Now, modern ham radios will also have one of these, and you put up your GPS thing, and that way the frequency you're on is exactly the frequency of the guy you're talking to. You don't have to have that, but the nicer ones do that now. Okay, now you can buy some inexpensive ones. So these two, the green one and the black one on the back, are ones from AliExpress. And actually the way they build those is they take surplus cell phone towers, pull the GPS DOs out of them, and then put them in a box, sell them with some extra circuitry. But for something you could buy, they work pretty well and they're inexpensive. Now the little box there, the mini GPS one, it says, is one a guy in the UK builds, and that's what I have in my home lab to check the frequency stuff. And then down at the bottom is one for a calibration lab, or let's say you have some sort of lab where you have to have frequency exact. And the reason you have these crystal oscillators is if you lose the GPS lock, the OCXO, it stays on frequency until it gets another lock. And this lab one has a double oven OCXO. So the oven controlled crystal oscillator and another oven for even more stability.
That's cool.
Okay.
How much are those ones on the GPS 10?
What, the ones in the upper right?
The one in the middle,
The one I did?
Yeah.
What you bought?
the mini GPS?
Yeah, that's about
Cheap,
$200.
it's not bad. It'd be good to have.
Yeah.
Okay, what's this circuit?
Now let's talk about voltage standards. Okay, what's built, what are the standards and what's built into your instruments? Okay, so up until 1990, the Weston cell was the standard, and it was a very specific battery that was set up so if you drew no current out of, the voltage was exact. And you used to be able to buy these, and you buy one and you draw much current out of them. They'd last about 20 years. And that was the standard up until 1990. And now they use what's called a Josephine voltage standard. It gives you many more digits of accuracy, but it's based on superconductors, and you can't do that at home. This keeps that. Okay. So what are the voltage references inside testicles? Okay. Because almost everything has a voltage reference in it. Okay, any voltage you measure uses an A to D or a D to A, and the best accuracy you're going to get is the reference. You're going to get less than that, but you can't get any better than the voltage reference you're using. So what years ago, the first solid state ones were what are called temperature compensated Zehners, and they were a specific voltage. And they made them a couple different ways. Okay, so Zehners voltages above a certain voltage, I forget what it is, have a positive temperature coefficient. As their temperature rises, the voltage increases, and that's from avalanche breakdown. If you go below a certain voltage, then it's actually Zener breakdown or tunneling breakdown, and that's got a negative temperature coefficient. And so there's just the right voltage that will get those two things will compensate out and give you about a stable voltage at an exact current. Or sometimes they'll use just the fact that the PN junction diode's voltage decreases with temperature and put that in series with a Zener. And that, okay, but they don't really use that anymore. Now, in most modern equipment, they use what's called a band gap reference. If you took an analog design course, they may have gone over how, do you teach band gap references? Yeah, okay. So that's typically what's in most things. Okay, and you could buy those off the shelf, and then you could, just off the shelf. Those are 0.05% are the best ones, 5% are the real cheap ones. Okay, so but that's the reference. Okay, so then, but those aren't accurate enough. So what they came up after that is they then took these buried Zehners and built that into an IC along with the heater. So the heater and the buried Zener were kind of in an oven configuration. And then they can go to double oven references. Let's take a look at one of those. The first one was the LTZ 1000, which is linear technology, which has since been bought out by analog devices. Okay, but the LTZ for 1000 for quite a few years was the industry standard voltage reference. So the little voltage the voltage source you have on your bench, those HP meters, yeah. This is what they have inside for the voltage reference. Okay, they don't make those anymore, but Analog Devices makes an equivalent part. It's slightly better. And this part sells for about $10. Okay. And so a lot of the circuitry is external. So it's got these two transistors, the Zener and the heater in the can. And then so you can put that around there and you have to worry about that. And okay. And then you can put all that in another oven control thing if you want.
Just a really quick question about the schematic. Between ports 1 and 2, is that like a snake resistor?
What?
What is that?
That's the heater.
That's the heater. Okay,
okay, that's the
heater.
That's the heater. They drew it like that, but it's just a resistor that's dissipating.
Yeah. Interesting.
Okay.
I've never seen that symbol.
Okay.
That's actually kind of cool.
Yeah. Okay. Yeah. So most heaters are just resistors.
Yeah. It looks like a snake resistor. That's why I asked. So
yeah. It's
a symbol kind of looking like
without. Yeah. They keep it because that's what LTC originally put.
Yeah.
Okay. And historically, they just kept the same thing. Now there's a more modern part. Now the high end one, this is ADR 1001. And you can see now all the circuitry is on chip. Okay, and they're more accurate. And you can, depending on how you set the resistors on the output op amp, you can get approximately 5 volts or 10 volts. Now, these are very stable, but the actual output voltage can vary quite a bit. So most instruments have a microprocessor in them now. So what they do is when they calibrate the instruments, they'll measure what that voltage is, and that gets put in non-volatile memory in that instrument. So if you change out that part, let's say that part dies and you try and fix the instrument, it's not going to match. You have to you'd have to recalibrate that part. See, Now, down on the bottom left there, you see kind of the demo board that the analog devices sells. So you can see the parts there on the board, and then you notice they have it inside a plastic chamber. And that keeps air currents off of it. You'd be surprised how much changing air currents will affect the temperature of what's going on. Okay, so we'll go over a story later where stuff was very 10 degrees when the air conditioning switched on and off. So, hold on. Okay. So when you try and measure voltage with a scope or a meter, there's all kinds of errors that could creep into your measurements. One of the most common ones, and ones people tend not to think about, are thermal offsets. And that's where you have dissimilar metals. Where do you have dissimilar metals? Well, let's say you've got a nickel lead hooked to solder on a copper trace. All those metals are different. Every time you do that, you'll get a voltage step, depending on temperature. Magnetic coupling, okay, typically that stuff comes from, that's typically an AC thing, but you have a loop and there's leakage magnetic fields from transformers. There's transformers in, old-fashioned power supplies and switching power supplies, and those have leakage fields coming out, and those will go through loops in your circuit. Leakage currents. Inside power supplies, you can have capacitive coupling inside the transformers or interwinding capacitance. There's wide safety capacitors and switching power supplies, and all those can create AC leakage currents. And so any meter that's plugged in will have those to some extent. Okay, so something like, the HP meter, they've minimized those quite a bit, but less expensive meters, that may not be the case. Okay, so that one way to avoid this, if you're using a handheld battery powered meter, those leakage currents aren't going to be an issue. Contaminated contacts. Okay, so, dirt, okay, you could get voltages for that. They can be non-linear, they can be dirt, you can have oxidation. You can have oxidation on something that looks pristine. It could be just through 1 or 2 atomic layers thick sometimes, and you have trouble getting the contact. And so, if you're having trouble measuring it, maybe take the probes in, or you buy hard sharp probes.
Buy sharp probes.
No, you can actually, let's say, there's a ProMaster or Pomoda makes hardened sharp probes that are really good. Okay.
So we had some issues like that when I was at Moses as a research assistant when we were doing some testing, actually, even on the IC.
Okay, so on ICs, okay, they actually make tungsten probes so you can dig through that stuff.
So
I'm gonna talk
that's
about
why
that.
that's why I was like, oh, I've been there.
Okay.
Because there's a lot of oxidation that happens around your pads.
Yes. Well, yeah, because you had aluminum pads. Yeah. Okay, so where we're doing TRW or Northrop, most of the stuff was gold, so it did.
Yeah.
Minimal oxidation. I can't say gold doesn't oxidize.
It's still, there's still some stuff.
Yeah, they're pretty minimal though. Okay.
When you're doing the testing, I know you mentioned like dirt and stuff. Do you ever wear gloves or take precautions into doing? I know like here, obviously dirt can get in stuff. It's not like very exact or anything, but
it depends. So if you measure, so what matters is, let's say you've got a circuit that's doing really low currents. Okay, just crap on the PC board. You could get leakage current, surface leakage on the order of hundreds of picoamps pretty easily. Okay, so you have to be very clean.
Like how, if there was dirt on it, other than scratching, is there any type of chemical you could use to clean? Recommend?
So pure isopropyl alcohol. Not the stuff you get from the drugstore.
Like with a very clean swab or some type of.
Do that, but you get like 99.9, and that almost evaporates away.
Just right away, so you don't even need to swab.
Yeah,
so
yeah.
just a squirt.
Or flush it. Okay.
Okay.
Okay. There's solvents.
Okay.
Okay.
Good to know.
But ideally, you keep it clean to start with.
Yeah.
Okay, and so typically stuff where that matters, that you do in a clean room or under a hood, where a laminar flow hood. Ground loops. Okay, so ground loops is, all your instruments are grounded. OSHA requires that. Okay, and so you hook stuff up, but you have these loops now that pick up magnetic fields, can couple in, stuff can pick up, and if you're plugging stuff into a wall, sometimes different in an industrial setup, different plugs will be on different circuits. And so you plug in one place, you may have loops going all the way back to the junction box. So in general, on a test setup, it's better to get one good sized power strip and plug all your instruments into that power strip and then plug that into the wall. And that minimizes the pickup on that test setup.
Okay. Just one big wall one.
Yeah.
Right. That's what we try to do here.
You try. It doesn't always work.
Yeah,
and somebody comes along and screws it up.
Yeah. Nathan's aware.
Okay. So RFI, so radio frequency interference. What does it come from? LED lights are notorious for doing it. Switching power supplies. Wall warts. You know the wall.
What's a wall wart?
Wall wart is the little brick power supplies you plug into the wall. They're called wall warts.
I have never heard that.
It's just another switchy power supply.
That's funny.
Power bricks. Okay, again, switchy power supplies. They radiate stuff. Cell phones. Okay, you go into a test lab where they're doing RF. They actually don't let you bring your cell phone in.
You just reminded me to turn off my Bluetooth because so I don't always have it on.
Well, no, you put it. No, you need to.
No, you just reminded me right now to turn it off.
Yeah,
I like to turn it off when I'm sitting. So.
Yes, or at least airplane mode, but even as a
just
computer.
Leave it out.
Okay.
Leave it outside.
Okay. Nearby radio and TV stations. You'll pick stuff up from them. Okay. Cell towers, again, the radio broadcasts, they put out a lot of energy. And sometimes if, let's say you're listening on audio and you'll hear like a click, 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 and then faintly, that's the cell tower or your cell phone talking back. Computers, all the switching, they put out a lot of RFI. Okay. TVs and monitors. Okay. You've got that big screen and all the digital signals going through that radiates lots of crap out of it. Okay. And then old fashioned TVs, which you don't no longer use anymore with CRTs, had big coils to steer the beam, and that would put out magnetic signals. But if you're getting noise in your signal, your circuit, don't blame that first. Look around. One of the ways to make sure it's not in your circuit is you build a chamber, a box, this Faraday cage, put your circuit in a box and then, feed something through and look at it.
What would you suggest just using for the Faraday cage, just aluminum foil or what would be the cheapest and easiest?
What actually works good for a cheap one is like a tin cookie box.
Oh,
okay. So not only is it an electrical shield, it's a magnetic shield.
Okay.
And then you sand where it comes together so it makes contact. Okay, that's a cheap one, and then you can put connectors in there.
That's actually kind of cool. Just put it right on top of your.
Yeah. No, that's a real inexpensive one.
That's actually smart. Okay. I'm starting good to go.
Okay, I stole that idea from somebody else, okay? Most good ideas you steal from somebody. Other places.
No, that's good.
Okay.
Just pass it along.
So actually, there's some very old national semiconductor papers where they talk about actually these those. Okay, and then they make shielded rooms where the whole room is.
Yeah, we have one here in Vivian Hall too.
Okay. So interestingly enough, in the older shielded rooms, they only use incandescent lamps.
Okay.
But they don't make those anymore.
Yo.
Okay.
So Melissa.
Okay, so fluorescent lamps, which are always going away, also produce stuff because there's some RF oscillations in the plasma inside, besides just the AC stuff. So typically what they do now is they'll have LED lights inside the room, but they supply those with DC power. So they actually put the power supply outside the shielded room, and they'll build a DC supply and filter all the stuff out and just feed DC to the LED lights inside the shielded room. Okay, but you're never good. You put computers in there and stuff, but at least you can minimize stuff. Okay, and here I didn't talk about if you're in an industrial thing, motors, how, you know, somebody else starts a motor, stuff in the next room, vibrations. Okay, you're in a building, okay, and somebody's working on something, pounding on it. Okay, there's also stuff if, I didn't hear, there's piezoelectric sensitivities, ceramic caps, many of them are piezoelectric. So if they actually, if they get a shock, they'll produce a voltage. So one way to do this, most oscilloscopes, if you go up to the oscilloscope and put it on a sensitive setting and tap on the input with a pencil, you'll actually see little things going around, traces move up and down. And that's actually just it vibrating the capacitors inside the oscilloscope. Oops. Thermal EMF voltages. This is what screws you up when you try and measure small voltages. Okay, thermal EMFs arise at the junction of dissimilar metals. Okay, it's the way thermocouples work for measuring temperature. They're two metals. But where would you see this? Copper to solder on PCBs, solder to the component lead, switch contacts, okay, relay contacts. So in precision instruments where you're trying to measure tiny voltages, if they have switch contacts in them, they'll actually machine the contacts out of the same piece of metal so that the alloy is the same. Okay, and so bond wire connections, probe connections, all these will give you offsets. Offsets are typically, you'll see in most things, are typically on the orders of microvolts, can be much higher than that. Okay. Now, there's these op amps you can buy that are called zero offset op amps that have choppers in the side. And typically, those will get you offsets on the order of half or microvolt or microvolt. You go, well, I need more than that. Chances are you can't get anything better than that anyway because of the thermal offsets in your circuit. Okay, so and these happen. These are so let's look down at the bottom here. So at the bottom here, I've got this is a surface mount resistor on some copper traces, and it's soldered down. Okay, so you got copper to the solder to the contact on the resistor. Then you have the opposite thing going back. So you have one step going back, one going the other way. So normally the voltages would add one way, then subtract the other way, and that's not an issue. But now let's say you have a thermal gradient. You have a temperature difference across the board. One side's a slightly different temperature than the other temperature. There'll be a thermal offset voltage generated by that. Okay. Yeah, and typically in most stuff, that's ones of microvolts, maybe tens of microvolts, but it can be worse. So here's an example. Your guy took a multimeter. This is on, like, say, a 20 millivolt range. So everything below the distance. So here he's hooked an alligator clip to the probe. Now he just puts a hairdryer on it. 176 microvolts. Okay. So when you see, anytime you want to measure stuff below millivolts, you got to worry about millivolts or tens of millivolts. This stuff starts coming in. And normally people don't think about this, but this will screw you up every time if you don't think about this stuff. Okay, now let's talk about meter accuracy. Okay, so this, okay.
If you need me to switch over to the overhead too, just let me know.
Okay, okay. So here, so this is an example. This is the meter that's on your benches over there. This is kind of an industry standard meter. These exist in almost every company. They still do it. Okay, and so the accuracy. The accuracy on different ranges, the way it's specified, is in that table. So it's got a reading accuracy and a range accuracy. Okay, so you notice the top range is the 100-volt range. Okay, and so let's look at the 10-volt range, which would be this green one. Okay, so if you look up at the top of the range, it's going up, and we see that the range accuracy is 0.004%. And so you can see it's bending over, and that asymptote's going to go up, get to about 0.004%. That last line is 0.001. So but as you go lower and lower in voltages, the accuracy of the meter goes down. Okay, and the flat part's really limited by the range accuracy, or what percentage change there is of the range. Okay, now these accuracies, this is what they guarantee. Typically, it's better than this, but this is all that's guaranteed. And when they send it to the Cal Lab, they measure the meter within this. They call it good, send it back to you. Now, if you take 3 meters and you measure the same voltage, you're going to get 3 different results. And they're all right, because they're all within their accuracy reading. Okay, now if you look down, you'll notice these are equally spaced, but when you get down to the 100 millivolt reading, that one's not as close. What's causing that? The internal thermal voltages in the meter. They can't. Okay, that's why that one's. So this is now this is a high end. This is a high end handheld meter. This one.
Let me put it. Oh yeah. Do you want me to put it on the overhead at all, or?
No. The picture's there. I'm just showing here.
Yeah.
I just brought them along for show and tell, so after class people can come.
We can play. Okay, cool.
Okay, and this is a very good meter, and you can see here, and on most meters, they'll give you it's 0.02% of the reading plus 2 digits. Okay, anytime you have a digital display, it's always it's always plus or minus 1 digit on the last digit. Yeah. Okay, so they specify plus or minus 2 digits. Okay, so let's say here we're on the mid range, which is the 50-volt range, and we want to measure, and we're measuring 10 millivolts. That's a 10% error of it. Okay, and that's just because, so the key thing on all of these is the meter's most accurate toward the top end of the range it's measuring at. So is there questions about these graphs and how they work? So the error lines are.
It's whatever your value is, and then the maximum possible reading error on it.
Yes,
right? So
and then the horizontal,
you get
the slashes or the percentage error at those readings.
Between those points, and you can see how bad it gets or how good it gets.
Yes, okay, and
so basically the smaller it goes, the more possibility of error.
Yes.
Because of the digits.
So these are something I came up with for this lecture.
That's
I've never
actually
seen
really
these
nice.
graphs before. Typically, you just see these tables.
I mean,
and you don't get a good feeling for what's going on. And so,
Yeah, usually we're in like the millivolt range when we're testing things in like 202, for example, so we can kind of find out there where our maximum reading area is.
yeah,
That's cool.
okay, so down here. Now here, so this meter, the meter I just showed you, that meter is about $300. Now, this is the meter that I have up here. This is my desk meter, the one I keep at my desk and on my lap. These are about $16.
Yeah. But they're
Okay.
handy.
And it's good enough for most things. Is the battery voltage there? Is there a voltage?
I've used this one on my car, for example.
Okay, yeah.
Just to make sure, like what was.
Yeah, that's fine. That's a 0.5%. So all these are on the same scale, so you can see what happens here. So you can see, it's 5%, 0.5% error at best. But you really want to be on the upper half of the scale on these. So this is just kind of an interesting illustration. Okay. Now we're at, I'm going to talk about your battery is running low. Is there a power supply for this? Your computer's about to die.
Oh, it's right there. I'll do it. Sorry, it got unplugged because I went to the bathroom in the previous section.
Yeah, so yes.
Thank you for telling me before.
Well, it just,
Good. It's ready to go.
yeah, I don't want this to.
Yeah. This will solve the problem immediately. You can say, okay, sorry about that.
Yeah, okay. So if there's anything you get out of my lecture today, this is the most important thing I'm going to talk about today. Control parts are golden standards. What's a control part? A control part is used to verify that the test set is measuring consistently and repeatable results over, okay. And control parts, anytime you set up any kind of measurement that's going to run over an extended time, production tests, some sort of environmental test where you're testing how environmental things affect it, burn-ins where you're burning in a component to make sure, so you want to test it before and after, reliability tests where you're stressing a part over time. You want to have a control part, okay, and what the control part is measured every time you do the measurement to verify that the test is consistent. Okay, control parts are only used to verify the test set. Once you have control part, you only use them for that. You do not use them for anything else. That's why sometimes they're called golden standards. Okay, if you monitor your control part measurements over time, that will characterize the repeatability of your test sets. Okay, and then control part measurements are best done at the beginning and end of each test session. Okay, and then down at the bottom, when you present data, you should show the control parts data your control part measurements for your test set every time you present data. That gives people confidence in your results. If you don't have control part data, and you're showing results that people deem as not favorable, they're going to attack the credibility of your data and your credibility.
Your credibility.
They will. Okay. People get very defensive when they're seeing stuff they don't. Okay. There's politics everywhere, whether you like it or not. Okay, so it's important to understand the control part data and make sure you use it wherever you can. So what can change between tests? Contacts, connectors, or probes could change. Let's say, you're making contacts with wafer probes. You've got a fixture where you're putting parts in and taking them out. Those could get damaged. There could be contamination. Cables, cables move. They can break. or worse, they can be intermittent. Position change in RF cables. Okay, if you move RF cables, their phase delay can change slightly, and that can screw you up. So in often critical test sets, you'll use rigid coax cable because it doesn't move. Improper connections. Let's say somebody pulled the equipment out to take it for calibration and brings it back, and they hooked it up wrong. Interference sources. You're getting some sort of interference. Okay. Again, the test was working fine, and then somebody set something up down the hall that's sending stuff out, screwing you up. Test equipment gets swapped out for calibration. In general, if you have some sort of test set that's being used in time, you don't want to swap test equipment out. You want to keep that same piece of test equipment, and when they check the calibration, put it back in. Don't swap it for another, because again, that one will be the same. You put it in another, it will be valid, but it'll have some sort of shift, and that shift will show up in your data. Borrowed test equipment. This is when somebody comes and nabs your test equipment and you don't know it. You have to go find it and put it back. You don't know what they did to it in the meantime. Temperature. The temperature's changed of what you're measuring or isn't controlled. Operator. Sometimes tests depend on who's running them. So when you have tests, you want to record who the operator is. It's part of the test data, always. Power connections, like I talked before. Somebody unplugged one of your instruments and plugged it into a separate circuit from everything else. You didn't know it.
So we started taking, in this section on 599, we started using lab notebooks. So when we do tests, we write down all this information. And if there's any nuances with the changes in the test that we do. And what we're gonna do is those lab books are gonna get passed on to the next iteration of the class. Like when there's like an ADC and someone's testing it, then the next generation can go back and look at how those tests were done on the same circuit.
Yes, but
So
let's say
history to see.
that's good. But let's say, but you want to know that, sometimes you have to move physical location. Okay.
Yeah. And everything changes.
The lease is up on your building. They move you to another building. You got to tear the test set out and move it.
Yeah.
Vibration. There's construction happening down the hall.
Or you're on the second or third or fourth or fifth floor of a building.
Yes. Okay, control parts don't always pick up intermittent issues, but they're good. They're good for showing stuff that's going on.
Did you put time of day also? That was one of the problems I had once, was the time of day.
I didn't. I was going to go into what should be put in test files, but I didn't do that slide. But you should actually record date and time on every set of measurements as you make them.
So
always.
One time I was doing some testing on some RF equipment, and it was working great when I was at night doing it. And the next morning when I was going to show my boss, it didn't work. And it had to do with the fluorescent lights being on outside in the hallway.
Oh, yes.
And it was nighttime and all the lights were off. And I was like, everything works perfect. And then the daytime I go and I'm like, come here, look, it's working. And all of a sudden it wasn't working because we didn't have like a nice room to be able, I should have used a little tin.
Okay. So now here's the story. This is actually one of the last things I worked at Northrop Grumman before I left. Call it the case of the Drifting VCO. Okay, so space flight projects require high reliability.
Absolutely.
Okay, you can't go fix something once it's up.
You can't fix it once it's up.
Okay, most components go through a burnout to weed out early failures. After burnout, a subset of components is taken out of all the components you burned in and put through an extended, they call it quality conformance inspection or a QCI test. And typically they're run at an elevated temperature for 1,000 hours or, there's some sort of specified test.
What does QCI mean?
Quality conformance inspection. Okay, I didn't know that. I always heard QCI. I Googled it and I made that.
I was like, what is it? In most
it was just one of those acronyms I just always accepted.
In most companies, like after they have a model quality assessment to make sure your models match your stuff.
Okay.
But this is like something like the conformance of them.
Yeah, okay.
That's actually interesting.
Yeah, so you take all these parts. Now, all the parts have to pass this QCI test, or that lot of parts gets rejected.
So they have to go through it before they go into a piece of equipment.
The QCI parts don't go into equipment.
Okay, that's what I was gonna say. Isn't it already like used?
No. So the burn-in is everything goes through it.
But they test many of them to make sure.
Okay, so the burn-in is to get rid of early failures.
Okay.
Okay, so they run everything for, let's say, 1,000 hours at a slightly elevated temperature and test it. And anything, and that's to get rid of any early failures. Okay, and all parts do that. Once they do that, they take a subset of those parts and those go into the QCI test.
Okay.
And those get more extensive
Testing.
stress or testing. And that subset of parts has to pass for those other parts to be used. You don't want to do the extra stress on the part you're going to put in something. Okay. Anyway, so it turned out in this case, the VCO failed the change of frequency versus tune voltage test. The change was greater than the allowed variation, but all the other tests for the part passed. Okay. The manufacturer had no idea why that was going on. But I got called in because they are already having big committees of people looking at this.
This one part.
Okay. But it was my job to filter through the chaff and figure out what was going on. So the first thing I asked is, did they use a control part? And they told me yes. But I dug deeper and no, they weren't using control parts. Okay, and then as I dug through and looking at data, it turned out that they had one part that had failed the phase noise test after burn-in, and they had set that part aside.
So it all came down to money in the end.
Well, okay. Well, they didn't want to have control parts because the company didn't want to pay for parts they weren't selling.
Yeah. They didn't want to
because they wanted to save money. It ended up costing them more money than they ever would have saved. Okay, but all right, okay. So, but it turns out that, because there was this one part that had failed earlier for a different reason, I then later used that as a control part for future tests. Wow. So, okay, so I got in there. Everybody was worried the VCO was drifting.
So it's this one teeny part that's stopping a whole
space program.
Whole program.
A whole program.
That's like a one VCO. That's a big deal. And how many billions of dollars are going into this? A lot.
Yes.
Right?
Oh, yes. No, I had
one VCO.
Okay. Yeah. So
that's nuts.
Okay. So it impacted program schedule.
Wow.
Okay.
And the manufacturer couldn't get
and because the schedule wasn't being met, payments were getting made to the company.
Yeah. Can you imagine the stress?
The manufacturer wasn't getting paid because their parts didn't meet spec. Nobody was happy.
Wow. That's incredible.
Okay, so let's look into this a little more. This is a good story. So this was their test set for testing the part. Mm-hmm. They used programmable HP power supplies and a frequency counter RF power meter. No other meters were used. There was no temperature measurements. Okay, and then for the tune voltage went from -1 to +10, and they had this relay in between on the power supply to shift the tune voltage between plus and minus. Okay. I looked, I looked at the accuracy of the meters. The specified accuracy on the power supply really wasn't good enough for this test. They never even looked at that. Okay, as I had talked about before, when a relay switches, you can get different contact voltages, and those can change when it switches. Okay, it turns out the frequency accuracy of the frequency counter was fine. That wasn't the issue, but no control part was used.
incredible.
Okay, so hold on, that didn't change. Let's go here.
Are you allowed to say, did they end up using another manufacturer or what?
No, let's, I'm, okay. I'm going on. Okay, I'm not mentioning frequencies that, or manufacturers, okay? It doesn't matter. That's not really the key to the moral of the story here. Okay. So I actually, what I did is I worked with the manufacturer. And they didn't have to do what I said, but they were desperate to get this out. Okay, and so I actually had to fly and spend time there. Because okay, and so what I did is I had them add a meter directly to the V-tune voltage, so we know exactly what that V-tune voltage was. So it's really measuring a V-tune versus frequency curve. And so if that voltage moved a little bit and the frequency moved a bit. So if you download the slides, all that you don't need to take pictures of the screen. It's all there.
Everything is there. If you just go to Chris Grossman.
No, it's diver.net/USC.
Oh, sorry, .u. So
diver.net/USC. That's where you can get a copy of these.
/USC, yeah.
Get a copy of these slides. Okay.
And we'll get them and probably post them later.
Yeah.
Deep, do you want to do that? I think
Yeah.
Summer Deep will post them too.
Okay, so I had them do that, and then I had them add a temperature measurement to the part. And they used a PT100, which is a thermistor. I'll talk about these later. And they used another HP meter to move that. Okay. Then in addition to doing that, I had them, when they measured the parts, I had them turn the part on and let it sit for about 10 minutes to make sure everything reached thermal equilibrium. They weren't doing that. Okay, and I had them every few seconds measure the temperature, the voltages and currents during that time of just sitting there. And then I had them measure the temperature and the voltages for every step during the sweep. Okay, and then we did an additional 1,500 hours of QCI tests, stopping every 500 hours to do the interval measurements. And with the control part now, I measured the control part beginning and at each step. We had this other part I used. Okay, so what were the results? Okay, it turned out, that although I was worried about the spec for the power supply, it proved much better than its specifications and contributed a small error that really wasn't the big issue of what was going on. There was actually a bigger error coming from the relay. It was 5 to 20 microvolts, not millivolts. I should have put microvolts there, of shift. For every time the relay switched. Thermalization delay. It turns out it took about 5 minutes for the parts to reach thermal equilibrium. Okay, when they did their tests prior, they actually were testing them while they were still warming up. That was part of the issue they had. Okay, the temperature measurement clearly showed how long it took the parts to reach thermal equilibrium. Okay, also, it turns out any changes in the frequency versus voltage curve directly correlated with the temperature. So that was the issue, is the temperature was shifting. Okay, all the deltas of both the QCI parts and the control parts were correlated with temperature. And it was shifting. And it turns out that sometimes there were sudden changes during the test of about 10 degrees. And it's because it was near an air conditioning fixture that was blowing on it.
Wow. Wow.
Okay, so if a control part had been used, the original test still would have been bad, but it would have been obvious it was a test issue and not a problem with the VCO.
Yeah.
And that would have saved months of time. They would have known what to work on. you'd save months and hundreds of thousands of dollars. Okay, so, but exposing test issues like this is exactly why you need to use control parts in your tests. That's the moral of the story.
So in the end, were they able to salvage what they had?
No, the parts were fine. It was a
Yeah,
test issue.
you were able
Yeah,
to.
everything was fine.
You just had to adjust.
Yeah. No, the parts weren't moving. It was the test. There was nothing wrong with the parts. It was bad testing.
That's crazy.
The parts were fine, even though they didn't know that. The guy that had
They had
designed
no
the
idea.
part had left the company 15 years before,
Oh,
and nobody there had a clue. I knew,
Oh.
after looking at it, I knew more about it than they did.
Wow.
But that's a different story.
Interesting. Wow,
Okay,
that's a great story. Thank you
Okay.
for sharing.
but using control parts is, if you do anything, that's what I want you to take away from today. Now let's talk about temperature measurement. That's important.
Very.
Okay, so the key way to do, one of the easiest, most common ways to do temperature measurements is thermocouples. And thermocouples are just two different wires of different materials, and they're welded together at the temperature point. Okay, now so you could spend $10 or $15 per thermocouple, and to when you buy them, or you could get a little spot welder and just do it yourself. You cut the thermocouple wire, plunk to the spot welder, and you're done. It works just as good. So, and in fact, I haven't done it yet. I was gonna get one of those Chinese spot welders for doing batteries and try to make it. Okay, I haven't done that yet. Anyway, there's a thermal EMF generated at the junction. There's a bunch of standard types of thermocouples. I have that at the table at the right. K is the most common. Multimeters like this one here that measure temperature. We almost all use K thermocouples. There's connectors specifically for each type of thermocouple, in which the connections are made of the same kind of metal that's in the wire, so you don't get thermal junctions in them, and they're color coded. That's why there's colors in the table at the right. Okay, but the issues with thermocouples, they are metal. So if you connect them to something, they're going to conduct heat away or into whatever you're trying to measure. So if you sometimes I'll try and get the finest thermocouple wire I can if I'm measuring an electrical circuit with it. They're cheap and plentiful, and there's lots of instruments that will measure them. Okay, that's typically what you'll use in a test setup. Okay, the next thing is thermistors, which is basically just a temperature variable resistors. Okay, so if you look on, you could get NTC, negative temperature coefficient thermistors, PTC, positive temperature coefficient thermistors. There's nonlinear positive temperature coefficient thermistors, and those are what the resettable fuses are. So they make their resistors, and as they heat up, all of a sudden their resistance will shoot way up and act like a fuse. Okay. Anyway, so for uses for thermistors, you can put them in your circuits for temperature measurement. You can use the fact that they change with temperature to stabilize your circuit, or you could use the fact that they change with certain temperature to not stabilize your, to make your circuit temperature sensitive if you want. Okay, it's just, these are some of the uses. Now there's a specific kind of thermistor called a PT100, platinum thermistor. Sometimes you'll see it called a platinum RTD, and RTD just stands for resistive temperature detector. Okay, and people will confuse us. It's just a thermistor. Okay, so it's a specific resistor that's made out of platinum. Okay, and it's made to be exactly 100 ohms at 0 degrees C. It's the most accurate off-the-shelf way to measure temperature you can get. So you can see here, you can get, plus or minus, within 0.2 degrees pretty easily. where a thermocouple is a couple within a couple degrees. Now, most modern bench meters, like high accuracy meters, will have a PT 100 function built into them. And to get the most accurate measurements, you could do Kelvin connections to the thermistor. Okay, and then they also make PT 1000 ones. So this PT 100 is what that company chose to use for the temperature measurement when they added the temperature measurement. Okay. So now, oops, okay. So now often you'll want to put a temperature measurement inside your integrated circuit. Let's say you're building an integrated circuit. You want to measure temperature. Okay, the easiest way is let's say the foundry just has a temperature measurement circuit. You just grab it and drop it in. Okay, but if you don't have that, the smallest way is just a junction diode. If you put a constant current through a junction diode, PN junction diode, and this works silicon, gallium arsenide, indium phosphide, doesn't work PN diode.
Whatever your substrate is.
Yeah, it doesn't matter what it is.
So we taped out in like 180 nanometer TSMC CMOS.
Yeah.
You could do
Yeah, they have.
PN silicon.
Yeah, you can make a PN junction diode. Okay, now you want to pick a current that's above any leakage current so that you're getting the diode action, but not so high that you're seeing the series resistance of that diode.
Okay.
So long as you do that, the temperature coefficient is going to be almost exactly linear, not perfect.
Pretty good.
Pretty damn good. Okay. So the issue is it will shift a bit with temperature. So you have to do a calibration run for a given temperature. But it's a good way to monitor temperature. And the good thing about a diode is they're small and you can put it exactly where you want it in the circuit.
And you'll take the measurement right where the
Yeah.
delta VD is?
Yeah, well, no. That's the one to the left. This is a single diode.
Yeah.
Okay, now the one to the right is called proportional to temperature. This is a 2 diode measurement. Okay, so normally when you see these in textbooks, they give it to you as the ratio of the areas. Okay.
We have that in all the 348
Yeah.
microelectronics books when we start talking about.
Okay, I don't like that representation.
Yeah.
I actually prefer the ratio of the current densities.
Oh, okay.
Which is how I drew it here, because you can use the same diode and put 2 different currents through it, get the same effect.
Yeah.
Okay.
It's nice.
Okay, and the reason you might want to do that is, let's say you're doing stuff in the foundry. They may not allow you to vary the size of a diode. They may just have fixed devices you can use. Okay, and so really what matters is that, is the ratio of the current densities, which is a fact, and the current density is the current divided by the area. So, right, and so typically you want to keep that ratio around 10 or more. And again, the same thing applies. The currents have to be above the leakage currents, but below where the series resistance of the diode comes in, and then that works. Now this is, oops.
Sorry, my jumpy computer.
Yeah, okay. So this is just kind of a rule of thumb is what's the transition between treating something as a lump model and a transmission line? Okay, there's a region where you got to think about it. And typically, for me, I've always used a 20th of a wavelength, where a wavelength, where the wavelength is computed with the speed on your medium. So it's not the speed of light. It's typically about 65% of the speed of light, because that's how fast signals travel down wires and on PCBs or in integrated circuits. Okay, so if you look here, at the bottom I have frequency, at the top I have the length of line that's a 20th of a wavelength. Okay, and so here you're doing stuff at what, 2 gigahertz. So you're really looking and a couple tenths of an inch, anything longer than that has to be treated as a transmission line on the PC board. Now, sometimes you can get away with that, but this is where you have to start looking at it. And just because you can't treat it as a transmission line, it's still, you have to worry about just, you know, capacitance and inductance stuff, okay? But you know, you can, but if it's smaller than that, a lump model will work, where if it's longer, you have to either do a distributed model or a transmission line model, okay? Now, you know, now that's easy if you have, let's say, an RF signal or a constant frequency signal. What do you do with digital signals? With digital signals, it's actually the rise and fall time that matters. And typically, I didn't put it here, the rise and fall time measured from the 10% to 90% point. And if you look at, if you do a standard rise and fall time measurement on the scope, the standard ones are 10 to 90%. So you know, that's what you measure on the scope. Scope, you can set up subscopes to do other measurements as well. Sometimes for very high speed stuff, they'll do 20 to 80 or something. But if you take that if you take 0.35 and divide it by that rise and fall time, that's the effective bandwidth you need to propagate that signal. And that's going to determine how long something is that you have to consider as a transmission line. Well, often for digital signals, you treat everything as transmission lines anyway, because you need to, if it's fast, you need to match arrival times. So you'll see lines that'll be squiggled or something, because you want all the, you know, the signals that are generated somewhere else to arrive somewhere else at the same time. So it's just, so now I have less detailed charts. I was going to do some stuff about hooking up ICs, but one thing that you may not see are ribbon bonds. Okay, and so ribbon bonds get used in RF ICs because they have lower inductance than wire bonds, and also higher current than wedge bonds. I didn't really do anything on this. I just tossed the chart in.
That's really cool.
Okay, you need to know they exist. Okay, and they're not the same machines. They're used like wedge bonders. They're a lot harder to do, more expensive to do. But you know, if you're doing a 3 gigahertz circuit,
it's worth it.
Yeah. Okay.
Yeah. And so, are there companies that will do that for you, or?
There are, but most hybrid houses that will do, you know, that build RF hybrids will be able to do that. They'll have a wedge bonded sheet.
Okay, this is something that, so this is how you do higher frequency testing. This is something I was doing at Moses, or part of ISI for a while. So I'm glad you're talking about this. Thank you for having me up these slides.
Okay, so now we're going to talk about RF probes. So here kind of we have the tip of an RF probe. Okay.
Do you bring some? Oh my God, memories.
Okay. So where I used to work, they went through a lot of RF probes. And I gave Susie a tour of the lab, and her jaw dropped when she saw the box.
It had a box of like,
it was probably $500,000 of probes.
It was literally $500,000 of probes. And they, like, while I was there, they chucked one right in front of me. I was like, whoa, because they cost a lot of money.
Yeah, so I can talk about how much they cost.
Yeah, let's, and this is just ground source ground. There's
there's other kind. So the spacings on these probes are they come in 100, 150 micron and 200 micron pitch spacing. Where I worked at Northrop Grumman, they used 100 micron and 200 micron pitch. Most of the world uses 150 micron.
Yeah, you were just extra.
Well, I just whatever. Okay.
And on the right, that's basically your pads that you place down and lay out. So in like a class like 505, you could make custom pads like this.
Yeah. So this is actually a through calibration. So these are ground signal grounds, and then that's just a transmission line.
So this is the calibrate. So you could do like S parameters or stuff like that.
Okay. So now I'm going to have different examples we can look at. So here are some RF probing examples here. So you can look here. This is an RF prober, and there's four probe mounts. They come in from each side. So the left and right Okay, on an RF prober, when you talk to them, they'll actually talk, say, north, south, east, and west.
Yeah.
Okay, where the one on the right's east, the one on the
Yeah,
left
like
is
that.
west, or the one away from you is north. So here, the north and the south has DC probes, and these are putting the power onto the IC. And then there's ground signal, ground probes coming in with the RF signal.
And then you'll be looking through a microscope into it, and I assume you're manually placing them?
So no, so at the production lab,
Yeah.
so the IC, so they actually have a video microscope. You don't stand over it.
Yeah.
Okay. And so when they do when they do wafers, that the part of the process generates a map of where parts are on the chip.
So it's gonna be automated.
Yes, so
it's gonna
what they
test.
do is they have to align the chip on the
Yeah.
thing, and then they drop the probes on one chip and adjust those probes on that one chip.
So when they're adjusting, are they doing that from a computer or are they?
No, they do manually. You
Manually,
manually,
yeah.
yeah.
So I was that person that manually did it, which is scary.
Okay, oh, yes, it's easy. One mistake and it's easy to do $10,000 worth of damage.
And then you'll be looking under the microscope and you'll be like, what's wrong with that one
Okay.
tip? And you're like, oh.
Okay, so when I worked in the lab years ago, 30 years ago, I do it myself. In the
Yeah.
last 20 years, I walk in and I go, Tech, come here.
And you get someone
You
else to
do
do it. Because the problem is you're looking down, but you also have to be looking sideways because it has to do with the distance.
Yeah, well, the people that do it all the time get the feel for it, okay, and so.
So you get a feel.
Yeah, you get a feel.
absolutely-
If you do it all, if you do it all.
Once you learn, you've got that ability to do it forever, I guess.
Yeah, once you get the feel for it,
Yeah.
it's easy, but
Yeah.
I don't do it all.
Yeah.
I never did it all the time.
So before you use these, you have to calibrate. So that's what he was mentioning before. So there will be different types of calibrations that you do. And then you'll start your RF testing. So say you want to test like a signal going through, or you want to do parameters or whatever. So calibration first, there'll be calibration, a bunch of stuff that you do on the layout for that chip where you can calibrate, and then you'll move over to your actual test site.
Okay, so here's a couple other examples. The one on the left, you see there's an RF probe on the west. There's a DC probe at the north. And then on the east, there's an RF probe with a bias T at top. And the bias T lets you put bias on the.
And then you can tell the difference between the probes. You can see the gold ones, I guess, in the picture, or the RF probes.
Yeah.
Whereas the DC probes don't have all the fancy stuff.
Okay.
Like,
Yeah.
they don't care about high frequency. They're not as
Yeah.
fancy.
Okay, so and the DC probes, those can actually have coupling capacitors on the probe, decoupling capacitors
Yeah.
on the probe or not.
Yeah.
Okay. Now, they're not that good because you got all that inductance
They're
of
still,
the probe.
they're still.
Okay,
wired.
for your RFs, yeah, so, but still, you can do that if you need it. So the one on the right here, this is an RF probe on the left and a DC probe on the right. And they're probably getting the ground back
Yeah.
common with the RF probe. Okay, so yeah, here's some more examples. Left is DC probes, north and south, RF probes, east and west. The one on the here, the right is just DC probes, east and west.
Very cool.
And these are RF probers,
Yeah.
okay?
And before you guys go, it's worth taking a look at those probes, like show and tell, coming up and looking at
Yeah,
them, so you
I
see what they look like. In case you're interested in doing higher frequency design, because if you're in a company, somebody's going to be doing that testing for you, most likely, if you're in a company.
Yeah.
Unless you are the entrepreneur that makes their own company, then you'll be probably working with them to do that, but go ahead.
Okay. Anyway, so here are some examples of specialty probes. Okay, so these are ground signal, ground signal, ground. So these are, these are 100 micron spacey, see, or no. Or actually, these are, yeah. So the one on the left is ground, signal, signal, ground.
Yeah.
And the one on the right's ground, signal, ground, signal, ground.
So that's a 4 tip, and then that's a 5 tip, because there's a ground, there's a and then signal and ground. So you can see that there's isolation too between the signals.
Yeah, okay.
Much like if you take in 505, isolation between signals.
Okay, and so the probes on the right are higher frequency probes, the ones on the left. You can tell by the connectors.
Yeah.
Okay, so generally they're really inexpensive probes will have SMA on them, and those are good to about 26
So the
gigahertz.
one on the right?
Yeah, the one on the left, that's probably
Okay.
APCs, which are compatible with SMAs, but you're good to 40.
Okay.
Okay, and then there's smaller connectors, and they have coax connectors that go all the way down to 110 gigahertz that are really tiny. And as they get smaller, you go up in frequency, they get smaller because you can get if you go too high in frequency, you can get a high order propagation modes in the transmission line, just like you can in waveguide.
And were you gonna mention cost?
Oh, yes.
You're like, I'll be there in a second, okay. I was like, you need to tell them so they get it.
Okay,
Like,
yeah, so here's another these are like
those are cool.
dual probes. This is kind where each side's replaceable.
Yeah.
Here's a specialty probe where they have multiple RF ones on the ones. They're showing you different examples. This is interesting. This is a load pull setup. Okay, and load pull is they have step tuners in these things, and that's used for mapping. You can adjust the termination impedance of the RF circuit. And for nonlinear circuits, you may not know exactly what the best load and source termination is. And so you'll go through a load pull mapping, and it'll go through different parts on this. So let's talk about how much probes cost. So I talked to a friend at Northrop Grumman, and Northrop Grumman's a big company.
Yeah.
They get discounts.
So
if you go buy the probes, they're gonna be
discounted.
more expensive.
If you're at a company, usually it's gonna be maybe 5 times this much sometimes. I've seen but this was maybe like 10 years ago, so maybe prices have changed now.
No, it's higher if you're not.
I've seen about 5 times.
You just saw how many probes Northrop Grumman uses.
Yeah, they're going through
they're such a big customer, they get discounts.
And if you just wanted to buy like one set, they're probably gonna charge you like 10 times that amount for a company.
Yeah, they got, the question at Northrop Grumman is how many probes per month do they use?
To give you an idea, that's actually really cool.
Okay, so the single arc probes, 40 gigahertz, 50 gigahertz, 110. Above 110, there's actually waveguide that goes to the probe.
I've actually seen some of those. It's pretty cool.
Yeah. Okay, yeah. So because we actually at Northrop Grumman, they build circuits all the way up to a terahertz.
Wow.
Okay, and at terahertz, the probes don't even work anymore. That's a
it's a different story.
That's a different story. Yeah, the probes. So probes with waveguides get up to about 500.
Yeah.
Okay. So then there's dual RF probes around 1200. So a probe contact, the most current you could put through one is 400 milliamps, and I wouldn't do that if that's your only probe. Okay, so if you have an IC that you want to probe and you need more power than that, put multiple pads in it.
And then do it that way. So put them in parallel.
Yeah, so those DC probes I showed you, those were $200 $250 for each needle on those. Okay.
So we have some probe stations in the other room that we inherited from an old lab. So we have a bunch of DC probe stations in the stock room.
Okay, so let's.
So simmer deep, if we wanted to refurbish, then we'd be along the DC probe side.
Yeah. Well, yeah, so the beryllium copper is typically what the contacts are. Let's have the best contact resistance. And they're great for gold and most 3.5 stuff, which is what they did with Grumman. Tungsten is the hardest. That's good for scraping through stuff. And
scraping through things.
Yes.
Bring out the tungsten.
Okay. And they also make nickel.
Yeah.
Okay, so these are different things you can get.
I think the ones we have are just basic, like nickel or something.
Okay. Who makes the probes? RF and DC probes. Form Factor is the biggest maker. And they bought up a lot of smaller companies and killed them. Okay, so to keep the prices high. They bought up their competition and just killed them.
Wow, really?
Oh, yeah.
Is that like a recent kind of thing or just over the years?
Over the years. Okay.
They knew what they were doing.
So yeah, so they were originally Cascade Microtech.
Okay.
Seuss and Lessie were big competitors. They bought them. They didn't just buy them and continue their lives. They bought them and shut them.
They just shut them down. They
Shut
didn't
them.
use.
They didn't
Wow.
still support any old stuff.
That's sad. Wow. Okay.
Okay. So GGB is another company that makes RF and DC probes.
Uh-huh.
They're in the US too. You can show that. MPI is in Taiwan.
Uh-huh.
Instronics is in China, and Micro Manipulators, another US company. Now, the probe stations themselves, Form Factor makes the probe station. Automated one. Semi-Probe is a newer company that was formed by the guys that used to be at Seuss. And we're looking for jobs. Once Form Factor bought them out, shut them down, they started. MPI is Taiwan, and they actually make really nice probe stations. Nicer than Form Factor,
Really?
less money. And
Cool.
the only issue is you may have problems once China invades.
Yeah. And at that point, who knows?
Yeah.
It's probably gonna happen. Yeah. Wow. Thank you for giving us all that.
So besides wafer probes, another thing that happens are probe cards. And let's say you're doing a mixed signal circuit.
Yeah.
You're typically going to have a probe card. And instead of having the wafer probes, there's a place on the probe station that holds the card comes out. Okay, and so you can get many contacts on there, but the problem is
Like
this is
maybe
all
there's like
one
100
probe. So you
connections.
damage one probe on this. That's what
Yeah.
the whole thing is like.
Then you have to have a new probe card. But you usually, this is not manual, this is automated at this point.
Yeah.
Usually.
Yeah, yeah.
There's a very big machine and what it does is it has the probe cards inserted and it picks it up, puts it down all
Yeah.
over the chip. And
Yeah,
then it will have a little piece of dye, it'll put a little mark where the chip's been tested like on that wafer.
well, no, you ink the bad ones.
Yeah, you can, or you can ink bad ones, or they have different color, and Moses, we had different colors for.
Okay, yeah. So
Yeah.
the wafer probers I was showing you
Yeah.
before, those were MPI wafer probers. Those are automated probers.
Yeah, oh, okay.
Okay, and typically for like commercial stuff,
Uh-huh,
they'll ink bad ones.
those do them.
They have, they didn't show you, there's a little ink thing they
Yeah.
put over it.
That's
Okay, so
interesting.
these are various, I'm just showing you these are very, so you have an idea of what exists. Part of, when you're doing something new, knowing it exists is half the battle. Once you know it
Yeah.
exists, you can then look it up.
Then it can be something interesting for you to look at.
So here's some more wafer probes. So here's a mixed signal circuit, and you can see the probe card, the probes are on the bottom, but there's a lot of support circuitry on the
Yeah,
top.
there's a bunch of stuff.
Decoupling capacitors or whatever. So some other probe cards. Here's some more probe cards. Anyway, this is what I've got for today.
That is fantastic.
Okay, and I brought here, so if you want to come up and look at the stuff, the meters I showed her here.
Before we
to
do
look at
show
some
and
of these
tell,
probes,
before we
the
do.
Kelvin probes. Yeah.
Before we do show and tell, I want to give you a gift actually from the class. Nathan helped get this. This is for you for the guest lectures that you gave. So we just wanted to say thank you for coming and teaching us all about everything. So it's just some fun things. But Chris, we want to say thank you.
Sure. Extra large is good.
Chris, we want to say thank you. Thank
Okay,
you
thank you.
so much. So.
Okay. Thank you very much. No, black.
Then come up and make sure you look at the probes. That's literally what they used in the industry. It's good to see them at least once, especially stand by for you. Just to have an idea.
Okay, appreciate it.
Thank you.
Okay, I hope you like that.
I know.
Love it. It was.
I know.
perfect. So I hope you enjoyed. Nathan, thank you.
I know.
Everything was great.
Yeah.
Yeah, if you want to.
So that's the red. Okay, yeah, that's why I came out, I was like, hey, that's delivering with my big shells. I mean, I have. My big
Oh, your
shells. Yeah,
shells.
it's just- Yes, yeah, but I'm still coming in tomorrow.
Yeah.
Say,
I
hey.
know.
Actually, I got 2 teachers This is my cousin that died young. She called it a lion teeth.
Anyway, you wanna come look at the
Yeah.
probes or?
So you guys come and look at the probes up here. I'm gonna put it on the,
They're all dead.
they're all bad, so you can't break
Yeah,
them.
you can't hurt them. They're already
If they
broken.
were not broken, they would not be like that, trust me.
Yeah.
It's not easier to take out.
No.
What I said.
It's
It's like,
PCB board for
it's
like
a-
$5.
that's, I'm saying
Usually you
if
can't
an
touch them with your
animal
hands,
he designs
obviously,
is
it's like this, so it's kind of neat just to see them. And then you'll see
gonna
like.
call
on
it a
here,
sport.
It's an expensive sport, you know why? That's what I'm saying, I'm saying, okay, I'm being
So it's not gonna hurt you.
Yeah. Yeah, so eventually they die from
Studied on.
that.
No, I agree.
Yeah.
Up and
So it's
down.
going up and down, and then
Up and
eventually
down.
they.
Like you can't fall.
Well,
Mechanical, I can just get this car.
Because that was like
But you said you get car parts, but you can always scour for
And you're
it.
like, great.
But you can scour
Crazy,
for those.
finishing it.
Okay, fine.
That was perfect. Yeah, so what are these?
Those are Kelvin clips. So you put these in the meter.
No, that's not the
Put it on
same.
4-wire
Oh my
ohms
God,
mode.
we need to get some.
And then you clip that on the resistor.
No, it's not.
And if you
The computer is on.
measure
No, it's not.
You give me the link for where you got it.
AliExpress.
You're at lucky.
I know what's gonna pronounce it, right?
And then here's some more Kelvin probes.
My dad has these, something like this. I've seen something. These are cool.
AliExpress.
That's really cool. I put it there, so it's on.
Yeah.
Okay.
So what you do, you
Yeah.
plug it into your voltmeter, put the voltmeter, put it in 4-wire ohms
Yeah.
mode.
No,
And
hold
then
on.
you
Hear me
use
out,
those
hear me out, hear me
to
out,
measure
hear me
a
out.
resistor, all the lead resistance.
Yeah.
goes to
Can you send it? Yeah.
I'll send you a link.
Hey, thanks for coming, you guys.
It is.
Here, this is my desk meter.
And you can put it here. This is still videotaping, so this
Yeah,
is on
yeah,
Zoom.
yeah,
so
yeah.
you're-
Yeah, this
You can see everything on here.
This is my desk meter. I like this one.
It's just sugar.
I can use that to check your phone.
Why is there a purple one? That's actually.
So can I have one?
It's so smelly.
Just to check something quick.
Yeah.
These are like 16
Yeah,
bucks.
let me clean
This
up.
is a real high-end meter.
It's
About
fake.
100. Let's see.
Well, I need to plug it in. I thought maybe there was a time, but.
Okay, I'll take
You,
it.
you need to just roll wait.
This is-
Oh,
It's fake fruit.
So just. You can look at the stuff.
I guessed what he would like, cause I.
See, that's what I didn't know.
They're broken, they're all broken. So that I wouldn't have.
Yeah, this is.
So these are ones, see, I told you guys,
Maybe I'll show them that really quick.
Typically, they just-
But the problem is,
Personality, bro.
I need to, actually. Okay. Oh,
So like, in that case, I'll take this and be right for that.
okay,
Okay.
perfect.
So you want to play with the oscilloscope now?
Yeah, the only thing I was like, come in, so we got it.
Let's go into the other room.
Yeah, hey Nathan,
Why you
can you put it in OHE 240?
What, this?
Yeah, yeah.
No, this one's like.
That'd be perfect.
The other one is like, it's a nerd model, it's like Amazon.
Okay, that's everything, Chris. Thank you for today. It has been a pleasure. You are always welcome to come back anytime you want. We enjoyed that greatly.
You can't even get a new phone.
Different perspective.
You need to spend
You have an absolutely wonderful perspective from like the real world.
Bro,
So
no, no,
I mean, I can do more technical
Yeah,
stuff. right?
why?
Equations.
I'm like, Dad
But I
wanted
think
me to
that-
buy it, and I said, this is the worst waste of money I could have.
Anyway, Simmer does only give me
They're so similar.
and use it as needed.
That's what I was complaining last night. I was like, guys, this is
Yeah.
expensive.
Well, hopefully you come back and you can do more in the future too and talk about different things you'd like to. Yeah.